Okay, now I think we can start to take into the other additional video. This is now chapter 13, which is very short. I need around 30 minutes, and how I hope this video will be a 30 minutes video. So let's start with the definition first, the vector valued function. So basically we learn on vectors in chapter 12. So if we have let's say we have a curve, the red curve C within this picture, with this picture here, okay? So we could define at every point of C with a parameter t, we could define a positions for each for each time for each variable t. We can define that as a rt is basically a vectors with three components, f, g, and h, which denotes the variable x, y, and z. Or we could write here as that. Okay, and then in terms of most of the techniques that we have in calculus, if we use that in space, in the curve space, or in the multivariable calculus, we can replace them and then we can make it into the vectors. So suppose that we have this r, and if we take the limit of r, which means that we're going to take the limit for each one of the components, or for each x, y, and z. And if, of course, if the limit is provided or exists. Now, let me get through the idea for, I will skip the introduction part because I would like to focus more on the derivatives. So in derivatives, let me write here, derivatives. In derivatives, we have the definitions, okay, on derivatives. So we could just change the old definition, which we have the f t plus h minus ft or fx in calculus 1. So we could change this f, the functions, with the vector function r, and this would be, it could be understood as, if we took this picture, so let's see this picture first, okay? So suppose that we have rt and we have rt plus h, which denotes the positions p and q, and then we could have these differences, or using the triangle law in vectors, we could have this rt plus h minus rt, that is going to be the vectors function for pq, okay? So we call this a secant vector of pq. So focus on the curve C that we are going to, this is our main curve, okay? This is our main curve, which means that every time we have a line that is cutting this curve, we call this line a secant. Okay, so this will be a secant. So secant PQ, or this two distance between this PQ, we could relate this PQ with the vectors using the vector positions of P and Q, okay, which is RT and RT plus H. Okay, that's the first thing. The second thing is, every time we are going to, for example, if we focus and if we want to know what will be the tangent at P, of course, as you know in calculus 1, this is actually similar. Notice that when we take this Q, getting closer to P, notice that all the vectors here, that is the secant, so this is the secant, so this is supposed to be secant PQ. Secant PQ get closer to P, which means that this point is going to make a closer distance to here, which means this distance here will be going to be 0. Okay, so we are going to take the limit by this definition here. As the distance is 0, which means the distance between the RT and RT plus H, right? Since the parameter is getting closer or getting 0, then we could define that as our derivative. Okay, very similar to what we have in calculus 1. We say this is the tangent vector r prime t. Okay, okay, provided, so this is supposed to be provided the r prime exists and r prime is not equal to 0. So then the tangent line to C at P, so this will be the tangent line, so this is the tangent line, so RT is tangent line to C at P. Okay, okay, and we could define this r prime t will be parallel to the tangent, or maybe let me write here, maybe it's not tangent line, so let me write here. So tangent line to C at P is parallel to the vector r prime. Okay, I think that will be better writings, okay, better definitions. So whenever we have RT, the short conclusion, or the very I think easy takeaway, is that every time we have a vector function, if you want to derive, so we derive all the components inside, all 3 components. So this will be a good way or convenient way to compute the derivative of vector functions for each component of R. So basically, this could be understood as all this F, G, and H, all of them, we are going to take a limit, and by using the same basic definition for limit, this one, we are going to get the same idea that this is all getting the proof. Okay, I didn't write all proof, but I hope you get the idea. Another idea is that we have this unit tangent vector as in vectors. We say this is T, with capital T, is r prime divided by the magnetic value of r prime. Okay, it's very simple, okay, according to the vectors. Okay, now next is I haven't prepared here, but let me just give you the picture here. I have prepared for you this one, and based on what we have before, then we can have this theorem, which I think I will try to solve the theorem for the number 4. I think I will just give you the example. So that will be this. So the formula for, if we take U and V as F1, F2, F3, and V is G1, G2, G3 for each of their component, if we take the dot product for U and V, U dot V, we have this scalar combinations, F1G plus F2G plus FDGT. Okay, so F1, F2, F3, G1, G2, G3, they are combined, and then we can write in terms of sum from 1 to 3 for FIT, GIT. So if we take the product rule, this will give you formulations for each one of them. Okay, so we have the sum of the fg, and then we are going to take it into our derivatives. So then, because this is going to be all the same within this f and g, so we could just write as u prime t vt plus ut v prime t. Okay, so basically this is just taking from here, which is this is very simple product rule from calculus 1, but we are going to arrange them in the dot product results, right? So this is going to be true, and from here we could write that the theorem here, that if the magnitude of the r is a constant, then the r prime will be orthogonal to rt, or for all t. So this will be true since this is a constant. So since this is a constant, then this will be true, that this will be equal to c squared. So this is a constant. Right here, this is constant. So by the dot product, and this, since the dot product for the if this is orthogonal, so we have 0 for the dot product. So rt dot rt, and we take the derivative for this dot product. This should be equal to 0, right? So this will be r prime t rt plus rt dot r prime t, which gives you 2r prime t rt. Okay, so that's why, since it's 0, this will be saying that so this will be, this means this derive here is 0. Okay, so it means that the r prime t dot rt, then it's true, it's 0, then r prime t is orthogonal to rt. Okay, okay, that's the idea. And then another part here will be about the wait, not this one, sorry, about the integrations. Okay, so the integral, let me write here the integrals. So the integrals we have as we prove, and I think we can start the integral by saying that since the definition for integrals, if we have the vector functions, this will be defined by the limit, okay, for each one of, and if we cut the curve, and then we can take the rti and then delta t. So this is actually mirrors the definition from calculus 1 integral, and then we move this into vector functions, which then give you the idea that whenever we have an integration of the vector functions, we could integrate each one of them for every component of x, y, and z. Okay, so another part of the integral that I think maybe I just want write as a review. If you have integral, and you can write in terms of the antiderivative terms, which is r, b, r, a. This is from the fundamental theorem of calculus. So we say that this will be the antiderivative. or perhaps not antiderivatives. Maybe this will be the result of the antiderivatives. Okay, result of antiderivatives. So this is antiderivatives. Okay, antiderivatives. Okay. Now, one more thing within the chapter 13 is the arc length. So suppose that we have a curve, and we are going to point the in between the curves. We put all the points, like for example here, 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 and then we are trying to connect all this point by taking this red line, and the smaller the distance in between those points, the line or the red color, it should be getting closer to the blue line. Okay, it could be similar and getting closer and closer. So let's say this is let me write here, this is about the arc length. So we are expecting to measure the length that we put the dots, right? So since we have the arc length, then we could start with, let me crop this first. We could start from the parametric arc length, which we have done this previously, and let me crop this again just to make sure that we have now here. And now if we take into the definitions on our vector functions, so we have now our definitions, and we can also simplify this in more clean way, that all this stuffs here inside the square root, this will be just the r prime t, right? The magnitude value of the r prime t. Okay. Remember that the magnitude value of the vector is equal to, this will be the f squared plus g squared plus h squared, right? So basically we have r prime, then this will be the f prime squared plus g prime squared plus h prime squared. Same thing. Okay. We write in terms of dx dt, dy dt, and dz dt. So we write this as a better and clean writings. I think there are another aspect within this arc length that we can elaborate, but I think I would skip that for a while. But maybe let me give you some idea what that's about. Okay, so that is actually about the curvature. That it is defined by, so the curvature is this, it is defined by the derivative with respect to s on the unit tangent vector. So t is unit tangent vector, which defines from the tangent or the first derivative in the vectors. So the curvature, this giving you a sense on whether the curve will be smooth or not. Okay. Smooth curve, determine smoothness of the curve. And we say the smooth curve, no sharp corner. Okay, I hope you get the idea. What does it mean? For example, here, if we have something like that, this is the sharp corner. Okay, that's not smooth. Smooth is something like So the way it changed for every period of t, it does well that it's not spike so much, but when it does here, it goes here and then suddenly go down. So it's like it's not smooth. Okay? The changes is not smooth, right? And from here is actually we can write with another formulations, and we could write in terms of the using the chain rule. We could write the curvature as the dt small dt, okay, small t, and then the s dt. And s is actually the length, okay, the length for each measurement between the point. So if we have suppose that this is the curve, so we are going to have every point here, let's say that's our space in between points, and this will be how the tangent will be changing. Okay, so it's fairly start quite straight, nothing too much change here, right? But then suddenly it changed quite rapidly, so it twists more sharply, and then here it goes smooth, nothing changed, and then goes really rapidly, changing really rapidly. So you can see from visualizations, you can see how the curve can be smooth and whether it's rough or smooth. Okay, and basically that is okay. And basically this we could also rewrite in terms of this is t prime t, this is the r prime t, because this is basically the s is in every between the points, which is the length of the line itself, which if we derive, that is actually our r prime, right? Our r prime. It's supposed to be separate like that. Okay. And yeah, I think I will end up until here. There's another advanced terms that is available in the curvature terms, but I think I will skip that. I will leave that as a additional materials. Okay, so this curvature actually additional materials. So as long as you know the vector functions, how to implement the derivative integrals, I think you are going to be fine. We are going to see this again in applications in at least chapter 14 and 15. Okay.